Welcome to the MatterHackers podcast. I am Dave, and I am excited to bring you along on this adventure, diving deeper into additive and digital manufacturing. Today, we are going to sit down with industry experts and talk about the reality of printing actual, real metal parts on your desktop 3D printer. MatterHackers goes to a bunch of trade shows, and I think the most common question I've been asked over the last decade is, does your printer print metal? And always our answer has been no. Like, no, they print a version of metal that you can polish and it looks like metal. But over the last year or two, BASF has come to market with actual real metal parts that sound like metal. They feel like metal. They are density of metal. They were actually stainless steel. And that really changes the game in terms of, having a great answer at a trade show, first of all, of does your 3D printer print metal? The answer is now yes. And it's not one 3D printer. It is now all FFF desktop 3D printers, whatever you probably have at home, can 3D print actual metal parts, thanks to BASF and their materials that they're offering. So why is this a game changer? And I genuinely do think it's the coolest thing in the 3D printing industry since sliced bread, if sliced bread was from the 3D printing industry. But I think that shows the sentiment of what you can actually do with your 3D printer that you have at home or in your workshop or at maybe you're a professional 3D printing. It's now possible to 3D print with stainless steel 316L or 17.4 pH from BASF, their line from Ultrafuse. And you print green parts, they get sintered, and they come back actual real metal parts. And that is such a cool sentiment to be able to succeed at that on this level. And the pricing has never been cheaper. In the past, metal 3D printing has really only been available on machines that are hundreds of thousands of dollars, which makes a per part cost of, $1,000 or more per part after you kind of think about all of the processes that go into this. And the FFF machines have been around for decades now and well established, but limited to thermoplastics. Where BASF comes in with some of their dark arts and magic is actually from metal injection molding. And if you know anything about metal injection molding, it is essentially injection molded material that gets injection molded, sintered, debound, then sintered, and it comes out as a actual metal real part. You encounter these all the time, whether it's in a cordless drill or a watch or some car parts or even keys. You've probably in the last week held something that has a metal injection molded sintered part in it in some way. BASF makes that material. They've got a lot of expertise here. They came to market with that material now in the form for 3D printing. And that's the real what's happening here and how it's so accessible is they took the magic of metal injection molded and combined it with 3D printing. And now you can, instead of injection molding your parts, you can 3D print them on your 3D printer. A couple little hardware requirements, we'll go over those later with Taylor, but generally accessible on every 3D printer. If you got an Ultimaker, it's already there's a material profile for it. If you've got even the cheapest of cheap machines, you're like an all-metal hot end and a geared extruder away from really succeeding there. Before we get too deep into it, I want to sort of clear the air and get some definitions out of the way. So obviously, you're going to be 3D printing what we call green parts. These green parts are essentially a hybrid of some metal powder in with a thermoplastic. And that's how you're able to print these parts that are very highly metal, about 80% metal, 20% thermoplastic, but can run through your printer. So from your printer, you will make a green part. Then it gets turned into a brown part. Brown parts are after debinding, but before sintering. So this is where the parts are weakest, and there are some design considerations that you have to keep in mind when the part is in its brown state, because it is so fragile at this point. Debinding. Let's just talk debinding in general. Debinding is when all of the plastic is removed from your part. So there's 80% metal, 20% plastic. We, through debinding, are going to remove that 20% of plastic. The final step is actually sintering. So after it's a brown part, it gets sintered. That sintered part takes the 80% material and condenses it down into 100% metal, 100% dense part. So it takes all the little bits and pieces of metal and fuses them all together, so you have like an actual metal part. So now with some of those definitions out of the way and an understanding of every desktop 3D printer that is currently printing thermoplastics is capable of this metal 3D printing, I think it's worth talking to some industry experts. And for that, we're going to go to Mara, and she's going to talk to a couple people that are actually using this, use cases that are real and in the world, and we're excited to share with you.
Thanks, Dave. Hey, listeners. My name is Mara Hittner, and I am Vice President of Strategic Partnerships at MatterHackers. I'm so excited to share this panel recording from IMTS 2020, exploring how Somerset Community College and L3 Harris are both breaking barriers of low-cost 3D printing with BASF 316L stainless steel. You'll hear about additive manufacturing certificate programs teaching how to print metal on $600 desktop 3D printers, and exactly how much time and money global aerospace and defense technology innovator L3 Harris saves by printing ultrafuse in-house versus outsourcing their metal parts. Listening to these leaders describe their processes will be super valuable. And if you would like to see the slides they are referencing, I know I get next slide FOMO, they are available for you at matterhackers.com/podcast. Check it out.
I'm super excited to be here talking about 3D printing with real actual metal on inexpensive 3D printers. So we have 3 stars of our show today for IMTS, none of which are me. Eric Wooldridge, who you heard is the director of the AM Center of Excellence at Somerset Community College. And then also Mark Holdhouse, who is the lead designer and additive lead at L3 Harris. And BASF Ultrafuse 316L stainless steel FDM filament. Eric, it is all yours. I give you my friend Eric. He's going to give you some applications for this process.
Good afternoon and good morning. As mentioned, I am Eric Wooldridge, the professor and director of the Additive Manufacturing Center of Excellence located at Somerset, but we're actually part of the entire state system. Slide for me, if you would, please, Mark. Click on over the next slide. And so we're actually part of a 16 community college system across the entire state. Next one. And we're located at the Somerset campus, and what our job is essentially is to get additive manufacturing out across the state through all of our 16 campuses. So what we do at Somerset is we actually build in the materials, the training, we test out equipment, we develop the curriculum, best practices to then get to the other 16 sites and help them to bring up the workforce. Overall goal, spread this skill set throughout the state and even beyond. Next slide. And to do this, we have to start off with one crucial fact. As we work with students, as we work with small businesses, we have to tell them this story, make sure they understand this above all else. Additive manufacturing is not really about the 3D printer. It's about the mentality. Because when we look at it, we see new materials, new technology, things like that changing every 6 months. We have a new adapter, a new upgrade, a new breakthrough, and so the equipment gets better and better and better. But the problem that we run into and what we have to really leap forward in is the mentality. Next slide. And to help people understand this, we tell them that additive is about next generation design. It's about next generation materials. And of course, that's what we're talking about today. But it's also about next generation production and automation. Being able to take the combination of the top two and turn it into production applications in a way that we have never had access to before. Next slide. What we also point out to folks is in terms of 3D printing, it is not about this. Keychains and trinkets, advanced technology, the ability to create generative design and lattice structure. I mean, the technology that is literally being used to make rocket engine parts is being used to make keychains and trinkets and poo emojis. And the fact is that's actually hindering the movement. Additive manufacturing is more about this. Next slide. It's about things we could never get before. Amazing designs and shapes that look like they were grown for a particular situation, not manufactured. I mean, you've got the new brake calipers by Bugatti. You've got the ability to actually create lightweighted parts, equipment going into space, lighter, faster, stronger, and you have the ability to set up production lines. You have actually literally military divisions setting up production lines for their supply chain breakdowns by just buying up benchtop printers to print what they need on demand. Next slide. And then, of course, you have this. The ability for us to just turn around and take a desktop model, $600 printer or less, and start producing metal parts right in the classroom, right within a small business. And these are true metal parts, which is an incredible breakthrough. Without having to do all the normal safety equipment, the training, the expertise, we can print on demand, and even all the way down to an elementary school level capability, which is amazing. Next slide. So I point out the number of I keep saying cost and low cost. We refer to that as LCAM. That stands for low cost additive manufacturing, because we point out that you don't get technology revolution by the top down, by the expensive equipment. It just doesn't happen. Let's face it. Google started with two guys in one lady's garage. eBay started because people had the access to a low-cost way to basically get rid of their junk in their garage. And so you don't get revolutionary ideas through high-end equipment. You get it through low-cost accessibility. And so that's what we push within our program, is we focus on the mentality with a low-cost equipment and then move up. Obviously, next slide. So that when the 316L came along, the UltraFuse came along, we were following the reports of it coming out, and just as soon as it became available on MatterHackers, bought up rows, because we saw this as the next huge step in low-cost additive manufacturing access. And so the first thing that we did, go ahead and flip to the next one, is we started printing with this. We started printing plates, parts, components, whatever we can do, and then turning around and doing typical machining and processing work on them. So we start welding the parts together. We start seeing how well they work. We start cutting them open to see what they look like on the inside. To actually turn this desktop printer into a metal printer that prints metal parts that we can do all sorts of other processes with. Next slide. All the way down to actually boring and tapping, to throwing it on a lathe, bending it, doing hardness testing. You know, we wanted to see how far we can push the envelope. And, you know, I know we kind of said stay within that 100 millimeter by 100 millimeter zone. We push it well past that, because at the end of the day, we want next generation products, and we want to see how far this stuff can go. So when this opened up an opportunity for us, we saw it as a huge chance to actually push this out across our entire state system. Next slide. And so we start producing all sorts of components and moving in that general direction. You know, everything from textured components, the welds that we push into, hit the next one for me, all the way to in place, print in place, moving parts. And we start showing it to the world and showing it to our students and technicians and small businesses and saying, you can do this, and this is where the technology is going. Next one. And we also kind of make the point that we don't just start from the top down, but we start from the bottom up in almost an infiltration mode. So we've taken all this low-cost mentality, we've taken the ability for folks to understand it, but we didn't create a 4-year 3D printing program, we didn't create a 2-year 3D printing program. We created a certificate, because we want folks who are in industrial maintenance, we want folks who are in engineering, we want folks who are going into surgical tech, we want folks who are going into machine tool, criminal justice, art, business and development. We want everyone to understand this technology. So what they do is they take their primary program that they're learning and planning on getting a job for, and we allow them to take a few extra classes and learn additive along the way. And what happens is they go to work, they get a job, and they take the additive mindset with them, and it allows them to turn around and bring additive to the workplace by saying, you know what, to their manager, this part that keeps breaking, perhaps an industrial maintenance guy has actually seen a part that breaks on equipment. He tells his boss, he says, hey, you know, we get a $300 or $400 printer, maybe $600 printer. I can print this part, take care of our problems. And that gets the ball rolling. That changes the mentality. And then that mindset starts to flow vertically, which is exactly what we want. Now, they may turn around and buy more high cost equipment over time, but it's the low cost access that makes the biggest difference. So we train the students that way, we train the teachers that way. We have teachers all the way from like the high school, college level down to elementary level learning it with this type of mentality. And then of course we'll go in and we'll train folks that are already in the workforce. You know, oftentimes, this is actually a couple pictures we took when we were training some folks from the DoD, and specifically their special response teams, to use additive manufacturing as part of their equipment gear and preparations and even logistics to doing what they do. So the ability to integrate additive at a low-cost model is the way to go, is the way to educate, and is the way to get small business up to speed and create this innovation we go for. And now we have the ability to do it in metal. And that's just a huge, huge step, not only for our state, but what we're pushing out for the nation and eventually the world, to bring metal 3D printing to everyone, and also incorporating the next generation design mentality of like generative, lattice structure work, the stuff that we're seeing with Fusion 360 and topology that creates these next generation components straight out of metal, tool steel, all kinds of things. And the opportunities for this are just unlimited. So that's kind of what we do, and that's how we kind of got into this space. You can easily check out material for what we provide on our social media. You can take a screen capture of this if you want, but I'm pretty easy to find. You can just say Eric Woolridge 3D Printing in Kentucky or SCC 3D Printing, and you can find all of our social media where we post out not only what we do, but also what's really happening in additive, because folks just don't realize what all is going on. Everything from the biomedical printing all the way to the aerospace components that are being made, even to the new vehicles that we have that already have 3D printed parts on them. So it's important for folks to be aware so that they're aware of the opportunities they get to take advantage of. So that's kind of what we did. That's how we got into this space. I'll turn it back over to you, Mara, to go from there.
That's awesome. Thank you so much, Eric. As you know, I am such a nerd for what you are doing here. It just blows my mind that this kind of education and this kind of technology is so accessible. I mean, you were telling me that you're using $400 printers and this material, which is what, like $60 for for 3 kilograms, something like that, or sorry, it's like $350, something like that. Which, like, you know, it's not PLA cost, but it's also not metal cost.
It's not anywhere close to metal. I mean, the fact is we can turn around, there's no way CNC and typical machine tool can touch this. For one thing, the waste ratio is ridiculously different. We don't have hardly any waste in additive. Whereas CNC, you take a block of material and you cut it down, that's all kinds of scrap you can't get back. But you also have the problem with, you have to deal with that in terms of a either recycling or hazardous waste situation, which even adds up the sustainability impact of that process. I mean, there's data upon data of the sustainability impact in comparison between additive and conventional manufacturing. So it's just unheard of to be able to do what we do and be even more efficient with the material in this case.
And then
Eric, I'm sorry, Eric and Mara. Mara, if you could go back to the slide showing the Bugatti Chiron brake pad. This was the star of the EMO trade show in Germany a year and a half ago, 2 years ago about, right there on the lower left of this. This was in 4 different manufacturing technologies companies' booths, because everyone was so proud of this. The company that printed it, the company that supplied the material, the company that machined it, and the company that sold the tools to machine it all had that brake caliper on display, because this is in a vehicle, I think it's $1.4 million vehicle that can go 300 miles an hour on the ground. And this is what stops it, is a 3D printed titanium part that can handle the heat and pressures to go from 300 miles an hour down to 0 in seconds. It's one of the more impressive applications anyone's ever seen from 3D printing.
And what I like to point out about that too is this, you know, Bugatti gets the contract going, gets the work going, but then you see immediately it starts getting this sold to Ford and BMW and everyone else. There's already other lines and versions of it on the market for other vehicles, and that is telling right there.
And I'm looking at the, the print farm there of the beautiful Ultimaker S5s, which are wonderful machines. They're around $6,000 each. But this print farm model is very much alive and well. I mean, from the MatterHackers perspective, we see people buying 25, 50, sometimes 100 of these inexpensive 3D printers to set up actual medium and sometimes high-ish volume production. Now you're basically setting up print farms like this only with $400 3D printers. Is that right?
It's a range. This particular one that we have is actually the French Army that set this up right in the middle of COVID. We do a lot of different ranges for that, and we are going for, and that's always what I go back to, is it's constantly changing. So it might be a $400 printer, one or 2 months is the hot item, and then the next it's a $600 printer. So we adapt the print farms as we build them across the state to whatever the latest and greatest technology is. But again, we're still talking about equipment that's generally under $600 regardless. Yeah. And you can set up volumes of these things. And then, of course, we are entering into this new phase. You can see this in the equipment being pushed out. The new phase of automation. You see what the Q3D systems are doing. You see what Quinley's doing. You see what the Creality's doing with these belt printers. The automation is the next step on top of what we already saw with volume printing. So it's a crazy awesome opportunity of low cost access, basically barrier removal for someone to take an idea to market like that. As long as you understand how additive works, you understand the mentality and how to use it to your best benefit.
And the other thing that's really driving this innovation is the innovation in the materials, and companies like BASF that are taking material that maybe previously was only available with injection molding and then actually making FDM filament that can be used by these open source 3D printers, whether it's a Ultimaker or a Creality or a MakerBot or whatever you've got.
Yep.
I know that BASF has announced that they do have another material that's coming out. Do you want to tease that?
So we got to have a cool conversation yesterday with BASF America and, of course, Germany, and some great guys that we got to talk with that have the same passion that we do. And there is the other grade of stainless steel coming out, a little bit more geared for tooling applications. And then there's more to come. We're going to be testing out and seeing how we can implement this quickly. As you see, we were already throwing welds to them. And to be perfectly honest, the welds are beautiful. We're seeing everything from stick and TIG working well. Next is MIG. And we're actually seeing that it actually welds better than typical stock stainless steel in terms of heat dissipation. So we're going to see a lot of opportunities come out with these new materials, and very, very excited about what's about to be possible.
Yeah. Eric, I just adore what you do. And I adore the fact that, we keep talking about it's accessible. Your certificates are through a community college. It's meant to be accessible. It's meant to be easily findable, discoverable, doneable by people of all ages, that whether they're looking to first get in, whether they're just coming out of high school or whether they're getting back into the job market, whether they want to upskill. It's just so exciting.
It is. And just wait till I have my middle schoolers start small businesses on their own with 3D printing. That's we're going to make that happen.
I'm going to be right there by your side, brother. Thank you so much for all of that. Mark from L3 Harris is next.
Thanks, Mara. A little bit about who we are. We're the Fusing and Ordnance Division of L3 Harris, and basically we design and build precision fusing systems, height of burst sensors, proximity sensors, penetrators. Our products basically initiate another event. So we have a lot of metal parts in our products, and we have a lot of electronics in them, and we interface with other systems within the other systems that we're integrating to. We've been metal printing with BASF material, the 316LX to start out with, and the L. We started in early 2019. In 2019, we partnered with BASF, Cincinnati, and DSH Technologies to work on successfully printing not only green parts, but also producing dense metal parts and tooling. Next slide. We developed a process that we use, and we use it internally to teach other people about how this process works. I think the thing to note that it does use metal injection molding technology for debind and sintering. So that's a well-established process that's out there, and we're going to go down this particular arrow as I speak. Next slide, please. For us at L3 Harris, the application of metal fused filament fabrication printing opens up freedom that's not available by other processes. Designers and engineers, they can concentrate more on their design as to what they really want it to be versus constraining that to their design plus having to look at what some of the processes that are out there that may not be applicable to what they want. BASF has design guidelines out there, and I encourage everybody to follow those because they're pretty good. We are printing wall thicknesses to 40 thousandths of an inch, 1 millimeter. If you look at the picture to the right, you'll see 100 thousandths by 280. But if you want to go like a 1 inch, then we expand that out to 185. So there's that ratio that we're dealing with when we're printing straight walls. 3 to 1 is recommended. We do go up to 5 to 1 in some cases. And again, uniform wall thicknesses. That does reduce the stress, not only in the printing, but also in the debind and sintering. And the 60-degree thing, we go 60 degrees. I guess you can go 50, but we've been sticking around at 60. And that's been working out very well. If you look at the lower picture on the lower right, that's an actual section cut through a housing. It has a 55.98 degrees on it. So that's a housing that a lot of our parts would fit into, electronics and spacers and things like that. And then there'll be a lid put on top, and that'll be laser welded around the unit just to seal it off. And then there'll be a connector coming out someplace on the side. That'll be laser welded in. Next slide, please. We typically orientate the parts as if they're going to be CNC machined. So everything is in the same orientation. We find that helps quite a bit. We do put side holes in, but we teardrop the shape and then go back and open them up if we have to. And they're scaled. So remember that it's 20% less. They always talk about 20%, scale it up 20%, but it's also 20% less than the build volume of your machine. So we've had some people run into that where the parts don't actually fit in a machine because they didn't count for that. Next slide, please. So in manufacturing preparation, we basically, we will copy our design model, or preferably we link it back to the design model. So we have a manufacturing model linked to the design model. When you update the design model, the manufacturing model updates. So that's been working out quite well for us. We prepare the model. We'll remove features that are best machined. So if you got close tolerance holes or something like that, we'll go ahead and remove those and put them in later. We add features to aid in printing, such as supports. We don't auto support. We generate most of those by hand because we found that to be more effective for us, especially for our small parts. And we plan for as little machining as possible. So we look at the part and determine what the orientation should be. We determine what the steps would be required to machine it if it was metal printed, and we use that as our process to move forward. Then we scale the model, and it's approximately 20%. And that of course is for the shrinkage during the sintering process. And then we generate our tessellated file for the slice software. Next slide, please. What we've done is we've generated a spreadsheet, and we track things so that we can really hone in the scaling factors on this material. We found that different machines in room conditions, sometimes the scale values may be different. We had our machine upgraded 3 times, and each time it came back, we had to go back and retweak the scale values because it was slightly different. So things were working different. So what we do is we start out, if you go on the left, the scale value, we'll start out with the recommended values. and we have our target part size, which is the block next. Then we print our part. We have a measured green part size, so we measure that. We send it out and get it centered. We measure the part that comes back. Once we get that part that comes back, we enter the other two blocks to the right of that, where the adjusted scale value and the adjusted green part value, those automatically update what we really should have scaled the part to. And so we use this quite a bit. Once we hone it in, then we know what the scale values will be for thin parts, medium height parts, tall parts, because we're finding those values are slightly different as we get into this. We also noticed that shrinkage can occur in the printed part and also needs to be considered for debinding and sintering. So we see that in our chart here, that just because we think the green part size, especially the height, should be a certain dimension, we're finding out that it does shrink a little bit in the machine as we print them. And we also know that it needs to increase for tall parts over small parts. Next slide, please. So once we get through the manufacturing preparation, we also are starting to use an FEA program that allows us to predict survivability in the brown part phase. So we're starting to use that, and we're finding that to be quite effective. So once we get all that done in the manufacturing preparation, then we do the 3D printing. Of course, again, it generates the green part size, and we slice the slice file, generate the program, the G-code program. Again, the parameters are a good place to start that BASF has developed. We're finding that the material dry is very helpful. It doesn't have to be, though, but we do keep ours dry, and we keep our humidity controlled in the room in the printer, mainly inside the printer. We've found that a heated chamber does help a little bit, especially on tall parts, for uniform layer thickness. Next slide. So before we get to here, a couple things I want to mention. We also add material to the bottom of the part surface sometimes, and then we machine that off flat with the top. So we'll add a little bit of additional material, flip the part over. We'll either machine the top or we'll sand the top flat. And again, the flatness is very critical. I think that was mentioned before, that the flatter your part is when it goes through the debinding process, the better off you are. And then for shipping, these parts are fairly robust. So when we ship them out to our debind and sintering house, we wrap them up in bubble wrap, and then we put them in a box, and we kind of line the box, and we send them out. So it's they are quite robust. So don't think that they're something that'll break easily, but package them carefully so they don't. We just shipped out 85 parts yesterday for debind and sintering. So catalytic debinding and sintering. This is something that I would recommend if you want to really get into the specifics of this, to go to your house that's doing that. BASF material is based on their catamol material, which requires a catalytic debinding, and that's in like an acid environment. So there's special machines that actually do that. And if you want the best results from your part, I would recommend that you go to a place that can do actually catalytic debinding and sintering. So in this particular case, where you're using DSH technologies, so if you want to know more about that and really get into depth of the process, I would go there and talk to them more.
That's actually who handles DSH handles if you get it from MatterHackers anyway, you get a debinding and sintering ticket that allows you to send in a kilogram of material, and that all goes through DSH. So everybody's on the same page on that one.
Actually, That works out very well too.
Yeah.
That's a really good offering you have there.
Tickets are great, right? $50 if you need an extra ticket.
$50. Can't get any better than that, especially if you're sending out 80 parts.
Yeah, but it's interesting though, because it's another thing to think about when you get a spool of 3 kilograms of material. Each ticket is good for a kilogram of parts. So, while maybe you have a print fail here and there, hopefully not. Hopefully you're, do your prototype of your part first in something in a PLA or something before you actually print with the BASF. But in theory, you put get as close to that 1 kilogram as you can in that box, and that's your one ticket. An extra $50 for an extra ticket, another, as close to that kilogram as you can get. Like, wait until you have that full kilogram. Quick pro tip, little hack for that one.
Okay, next slide, please. So in this particular part, this part shown on the picture here, we printed this. This has a lot of little leads that fit down in those slots and holes that are down in there. And they're also not straight going down in. They curve in different directions. We used to make this part by machining, and it was separated into several different parts. And this to make this part costs $6,000-7,000 just to get one of these made. And we're saving a lot of money, and plus we're able to add other features to it as we go along, and we don't have to go in and do expensive machining on a machined fixture. But for this part as an example, we removed some holes that were very close tolerance. We're talking plus or minus 1/1000th of an inch on some of these size of these holes. We did add material at the bottom for finish machining. So we, could you back up one?
Sorry.
Okay, so we did add material at the bottom for finish machining. The two large holes we used for alignment, and everything in this part measured out very well when it came back, and everything in that picture you're seeing was printed. So we used those holes to align it for finish machining, and it's worked out very well. Next slide, please. So here's the process, an example for this part. So we had the green part that we printed, and then the brown part, and then the centered part there. Material cost for this particular part each is $128.47, 19 hours to build, and the cost for centering we had $80. We went with your faster centering process that you guys offer. So
expedited service, fancy.
Goes to the top of the
nice
line. So that's this particular part. That was, like it said, once we got it back, then we did the machining on it. Next slide, please. Here's an example of another little part. This one's used to hold a electronic component with wires on it to hold it off of the circuit board when it's installed. You'll see in the design model, you'll see a slot in there. We actually removed that slot when we printed this part. We added a raft around it just to make sure everything was flat on the table. And then you'll see the printed green part with the raft removed, and then there's a centered dense part after centering. Again, the material cost was cheap, $20, 3 hours to make 4 of them. And of course, we paid $80 to get it centered. What they do when the part comes in is we EDM the slot in, cut the end off, EDM the slot, and then the bottom has to be highly polished. So they polish the bottom so that when it sits on the board and slides on the circuit board, it doesn't damage anything. We made these out of plastic before, but they didn't last very long due to the machine it has to go through when it does the actual soldering of the wires. So this worked out very well. Next slide, please. Here's a cost comparison for if we were going to machine these parts instead of 3D printing them. And you can see that our savings was $2,318. So you can see the cost there for material was higher, for printing was less for machining. Manufacturing cost was a lot less. Of course, we had the debind and centering. We did all 50 of them. And then our post-machining costs, which we went outside for that, but that was $2,500. So again, we saved quite a bit of money by making 50 of these. And these are an ongoing thing. So a lot of different programs use this on different machines out on the floor. So there's quite a few more that'll be made. Next slide. So we wanted to know how stable the process was, and so we took 6 of the parts that we printed on the previous slide of the 50, and we measured them. And you can see how close some of the dimensions are from part to part to part. Doesn't necessarily mean when you do your first part that you may not exactly be to the dimensions you thought you were going to be, but once you change your scale value and you maybe print another one to get to those tighter tolerance parts, which these are, then you can see the accuracy or the repeatability from part to part through the process. And the hardness values there are pretty good. There's one outlier there, but 35, but it's not a problem. So our goal is to hit a profile tolerance zone of like 10,000ths of an inch for up to 2 inches. So that's our goal. And here's another one, part for a fixture. This whole fixture is 3D printed. All the components on here. This does not go through the shop at all. There's basically no machining on this whatsoever. And so we print it and it gets assembled and the pins get pressed in. And the part that you're seeing that we printed, the metal part there, was plastic originally, and they kept failing, they kept breaking because you got to pull that back as a spring in there, and they kept snapping it off. So we went to a metal part on here, and that's solved our issues. You can see how the material cost there, the 8 sets, and what that cost, and it took 5 hours to print 8 of those 8 sets. So the threads are printed. So threads are printed on both parts, and the part is laying horizontal. You'll notice that because of the height ratio and the diameter, it will fail. It will fail in the debinding process if we try to stand it up. So we lay it down, and printing it at low layer thicknesses, we're able to achieve threads that the 2 parts fit together after they're sintered. And I believe that's it.
That is it. Amazing. Thank you so much. I'm so grateful that you are, while you're not able to show us where you are, that you're able to share with us what you're doing, and more importantly, how you're doing it. Especially those things like those the threads and the repeatability and the scalability of this is just hopefully very inspiring for other people that are maybe starting a business where they need parts like these, but they're inaccessible for their budget in any other way.
Yeah, we've printed parts here that are 7 inches in size of let's say it was a housing that's 7 inches by 7 inches by 2 inches tall, and it had all kinds of features internally in it. But we were able to print that and went through the debinding and sintering process fine. And but you got to follow the guidelines. You've got to follow the design guidelines.
Yeah, it's called design for additive, folks. Embrace it because it's coming.
Mark, I had a question for you. You mentioned threaded products. What kind of tolerances do you need for those threaded products, and did you need any post machining on those when you had to deal with threads?
Well, if it was going to be something that's used in our product, we would not print the threads in. This is a fixture component, so we don't really care. They go together and they lock together, and we're happy with that for fixturing. But if it's for a product, yeah, we would definitely machine the threads in.
Mark, you had on your comparison model for the 50 parts, you had around $1,000 of manufacturing costs. Can you elaborate to the criteria for what you consider the manufacturing cost of that $1,000?
Oh, that was for the time that we spent getting the parts ready, getting the parts in the queue, removing the parts from the machine, sanding the bottom of it off if it needed to be, prepping them. That's what that
built labor into that process too. Okay.
It's the labor. The machine ran by itself. we'll turn it on and just leave it on, and we go home and let it finish what it's doing.
Gotcha. All right. Yeah, that was what I was curious about.
I think, Mark, you mentioned, actually, it might have been you, Eric, who mentioned automation working its way into the additive space. I was impressed, I think it was 3 years ago at the Rapid Show, how much the ecosystem around additive is really building up. How many, instead of just having machines there, we saw all the component suppliers and the automation folks. I've seen some applications with an EDM built into the same case as the machine to cut parts off of the build plate. What are some other examples of automation you've seen that you think are going to drive this forward?
Well, to elaborate on that first, the backstory of all this automation is the number of folks that have popped up in small business that have just seen the power of the print farm. When you look at your Etsy suppliers, the folks, we have multiple companies that we've worked with that they learned early on if they design it for additive, they can produce it for additive, and then they can sell it with additive production. And what's happening is that they're in business, they're making money, and they're making product, and now they're trying to figure out how to optimize their time even more so. So instead of having to come in, we actually experienced this a lot during COVID when we were making thousands upon thousands of face shields. It was great. It was awesome. We did cycle time. We figured it all out. But the fact is, someone still had to come in and re-push the button and clear the plate. And that next step, the next leap, of course, is that the printer just runs and runs, runs. As long as you provide enough filament or production material at the onset, you can let this thing run for days and then optimize your time even more. So there is already a need for the automation because people realize, hey, I can produce even more with less of my time. So there's the motivating factor. So what we are seeing right now is that you are seeing the low cost model realize this space and say, okay, automation's next. So let's try a belt printer system. And the belt printer system generally is going to be, not only does it has technically an unlimited Z-axis capability, but it just prints and produces. It also reduces some of the leveling issues because the extruder never has to move but more than the X direction and the Y direction. So you have an improvement there. You're also seeing some of the other folks that are actually like, the Q3D systems, they're doing a new type of build material that actually holds so well that when you're printing, it's gripping and it's gripping tight. It holds it down. And then when it goes back to room temperature, it just releases and the part just slides off. And that is, of course, I think they're in beta stage right now. We're doing some testing with them as well, but that's going to be on the market. And then you're going to see more improvements like that. It's just the mentality has occurred that one person not only can run a bunch of production printers, but they may only have to come in once or two every 2-3 days. And, again, it goes back to that manufacturing cost, the labor of this, the labor of that. If you actually reduce your time to cycle yourself, then you're making even more profit. Some of the other folks that have talked to those who are actually doing this through Etsy and those kind of, modern platforms, they're talking about they're only getting maybe 60-70% of the potential production time simply because of human factors. And that's leading us to a whole other process, switching out from one part to the next.
Do you see the need for something the equivalent to a bar feeder in the CNC world for additive, where you'll have a magazine or something like this replacing filament as it's used to keep these processes going 24/7?
That's an excellent question. Your easy move is probably to switch over to the big rolls right off the bat. But the other catch is this: it's all of these exotic materials. Let's look at how many things are just coming onto the market, one right after the other. So I would imagine to take advantage of that, we're going to be still dealing with the filament model for a while, just because something new is going to be out there, and we want to try to produce with it. It's going to have better properties, so we keep adapting. And then as it matures more and more, then we will have feedstock. We'll have a whole new process there to go with it. I think we'll be dealing with the rolls, though, just because of all the cool stuff. And I often equate it to this. It's like the smartphone and the app. When we got the smartphones, then everybody became an app maker, and look at all that we have access to now. Now we have this platform that can produce, and the apps are the materials. The apps are these things that these chemical companies are out there creating day in and day out that are revolutionary in capability. And they're making materials that we cannot even use conventionally. You cannot injection mold them to save your life, but you can print them all day long. And so that's going to be probably the biggest driver of all this is the exotic materials and the exotic shapes we can do with this.
I'd like to thank our panelists, Eric Woolbridge, Mark Holthaus, and Mara Hittner. It's been a fascinating discussion. Thank you for your time this afternoon.
Yeah.
Thank you so
Thank
much.
you all very much.
Thank you. Thank you very much.
Oh, I can never get enough of those success stories. Thank you for listening. I hope that you found them helpful. Again, you can get the whole video presentation with the slides at matterhackers.com/podcast. Back to you, Dave.
Now we're sitting down with Taylor, who oversees our R&D and does much of the testing for new materials here at MatterHackers and has a ton of experience with this metal filament. And I got just some basic questions. Someone has a machine in their workshop. What are the basic hardware requirements for printing with BASF's metal materials?
Yeah, it's not super complicated. Number one is you need a hardened nozzle of some sort because it is abrasive. So brass is not going to cut it. Hardened steel, Olsen Ruby, tungsten carbide, one of those options that's out there. You need that. Number two is you need your heated bed needs to be able to reach around 100 C. Most beds do that, so that's probably not something requiring an upgrade or anything, but something to keep in mind. Also, important note on the extruder as well. It's a good idea to have hardened gears in your extruder to go along with the hardened nozzle so that you're not wearing out your extruder if you're printing a lot of this stuff. And then the last thing that's important is the actual bed surface itself. So the BASF materials don't stick to anything. The best options are glass with Dymafix, Captain tape with Dymafix are the two that we recommend most. There are some other glues that are out there that work well, but not as good as the Dymafix that we've had the most success with.
Yeah, that's worked pretty well. And here's an opportunity, because I've said many times that this material you can succeed and you really can print with, like, on a wide variety of printers. Are there any real limitations to the hardware?
Not really. It's quite a bit easier to print than, say, ABS. It doesn't warp as much, so a bit easier to deal with there. I've printed it on 3mm machines, 1.75, open machines, enclosed machines, big machines, and small machines. So it's pretty accommodating. The main things are, as long as you have the hardened nozzle, the appropriate nozzle, and the appropriate bed surface, it's pretty straightforward. The difficulty really comes in actually setting up your part design for success through the debinding and sintering process.
Right, the actual part design and its success or failure during the debinding and sintering process is likely more of a roadblock than any hardware pieces.
Correct.
Cool. We all love watching a first layer. Any tips of the trade for getting that first good layer and then therefore a successful part?
Well, the main thing with the metal, and it's going to not just be on the first layer but throughout the part, is that any air gaps or voids in your part are potential failure points through the debinding and sintering process. So while a first layer is important for every print, it's particularly important for the BASF stuff because it gives you the first look at whether or not you're extruding properly. If you see any little voids or gaps between your first layer lines, chances are you're setting yourself up for failure down the road. In terms of difficulties, it's pretty standard in terms of what you're looking for. The main thing that the adhesion can be an issue, but actually with BASF materials and the Dymafix, what is more likely to happen is that you have too good of adhesion, not bad adhesion, and the reason for that, the issue with that is that removing your parts from the bed becomes the tricky thing, not getting them to stick for the first layer. So there's tips and tricks for that, or ways to avoid that. But essentially, the larger your part, the more difficult it'll be to remove. And so you may need to employ one or more of those techniques for removal.
I have turned one part into two parts accidentally by removing it off the print bed.
Yeah, the nice, it's a good thing about the filament, but it can be bad depending on how you look at it. But it's actually really easy to deal with after you've printed. It's fairly soft, malleable, so easy to clean up with like a little X-Acto blade or sanding. So you can get that part really smooth and exactly the way you want it before you send it off for debinding and sintering. But because of that, it's also not that difficult to break if you're removing the part from the bed. You can, snap a part or break a feature off if you're not careful.
Pretty robust, a little brittle.
Yeah, it's interesting. I don't even know if I'd call it brittle. Because it's not like PLA in that it like snaps. It almost kind of just folds. It just will.
It's like a really tough clay.
Yeah, exactly. That's actually a good description.
You mentioned it briefly, but cleaning it up as a green part, much easier than cleaning it up as a stainless steel part when it comes back.
Yes, you do not want to be doing significant processing of the part once it's been sintered.
Which is totally doable. You can machine it, you can grind it and all these things, but removing layer lines, easier done in my clay analogy than it is in hardened steel analogy.
Yes, and unless you're planning to machine this part down on a CNC or manual lathe or mill, then you do not want to be doing any cleanup after it's sintered.
You've printed with more of this material, at least probably than any human in the United States. What are your couple just tips for success in the printing process and the debinding and sintering process, since you've got the most experience, I think?
Yeah, so number one, it's a mistake I've made early on, is make sure you scale your parts properly. Yep. I have both scaled them improperly or forgotten to scale them, printed, and then realized after that, this isn't going to work.
When you're removing 20% of the material that is the thermoplastic that allows you to print it, the shrinkage is significant.
Correct.
It's predictable.
Right. It is very predictable, which was shocking to me the first couple runs that I got parts back. I just was really stunned at how repeatable it was. The first parts that I designed to send off, I added a lot of slop or tolerance in it to account for it. It was actually a little planetary gear, and I wanted to make sure that it came back and was functional, so I gave it way more clearance than I normally would. But I did that. I printed that part twice, and both times came out virtually identical to what was modeled. So I stopped adding more clearance than I needed. But the main things to look for are really the basic guidelines that BASF gives, but they're more strict, I think, than most other rules with 3D printing. Thin walls are generally, there's a bunch of different ways to handle thin walls with FDM printing, and you can print thin walls with this material, but you're not going to get successful debinding and sintering with thin walls beyond a certain point. So just because it prints doesn't mean that it'll be successful in the debinding and sintering process, and that's probably the most important thing to keep in mind. You can't use support material, so anything that would require support material to print is not going to succeed or come out successful from the debinding and sintering. So you just have to pay attention to your overhangs, your overhang angles, or wall thicknesses too. And with that is anything that you can do to give yourself a little overhead from the recommended like minimums is going to go a long way. So I've seen customers have parts that they sent out that were like within 0.05 millimeters of the minimum recommended wall thickness, and they had a failure, and they bumped it up and they literally added 0.5 millimeters and sent it off, and it was successful.
Yep.
So that, you know, 0.5 millimeter is not a lot. It's a really small number, but it can be enough to make your part either successful or a failure.
Yeah, and I think we've seen it through users that have more experience, yourself included, is the basic guide that BASF has, and actually we have one on MatterHackers.com that's like a whole video that goes into a much deeper dive and higher specificity of some of the design considerations, how to clean your parts and all those things. But you can graduate and break these rules along the way. Model in your own support, for instance, that you will maybe later grind away. That allows you to gain some momentum there. But really for your first, I'd say 3 runs, stick to the basic guidelines because they're so powerful and well ironed out at this point.
Yeah, I would totally. That's and we did that, and as I got more familiar with the process and the printing, we did start sending off some parts with kind of different configurations to see how they would come back from the debinding and sintering, and then dealing with them in the post process. But definitely for your first couple runs, or at least the first run, you want to adhere to those rules as closely as you possibly can to give yourself the best chance of a successful print and post processing.
Right on. And like I said, for a deeper dive and more specificity, check out that video on the product page on MatterHackers. But thanks for your technical expertise, Taylor.
Anytime.
We'll see you next time. Thank you for listening. This has been Dave Gaylord with the MatterHackers podcast. See you next time.